Welcome to the deep dive. Today, we are strapping in for a session that really hits right at the core of cloud computing.
Mhm.
We're talking about designing systems that don't just work when things are calm, but can actually thrive under chaotic pressure.
Right.
For anyone building on the cloud or, maybe preparing for an architecture review, this deep dive is your shortcut.
Yeah.
You're tackling how to build architectures that are massively scalable and, crucially, loosely coupled.
And that second part, loosely coupled, that is so key. I mean, if you're leveraging AWS, but still designing everything as if it were on one giant server in a data center,
You're missing the whole point.
you are completely missing the strategic advantage of the cloud. Our mission today is to move past that centralized mindset. We need to focus on building systems that can grow, shrink, and, most importantly, the term that really defines a mature architect.
Fail gracefully.
Exactly. Fail gracefully. Without a single component's failure taking the entire operation down with it, that's the domain we're exploring.
Fail gracefully. I like that. It implies a certain intentionality in the design.
So let's start at the foundation of that. The multi-tier architecture. We always talk about web, app, and database tiers. Why is this separation the mandatory starting point?
Well, it forces the essential concept of separation of concerns.
Okay.
By splitting these layers, you achieve independence. Imagine a marketing email goes out and suddenly your web traffic just explodes, 10 times the normal volume.
Right.
But that traffic is mostly static stuff.
Sure.
You only need to scale the web tier. The expensive, complex application layer or the database, they can remain stable. You only pay to scale what's absolutely necessary.
And since we've separated our layers, we need a smart traffic cop out front.
Right.
What's the technology that makes this all work seamlessly?
That's the application load balancer, the ALB. It sits at the front, and it's constantly monitoring the health of all the instances behind.
So it's not just blindly sending traffic. Not at all. It routes it efficiently. But more than that, it acts as a barrier. It prevents any single instance from getting overwhelmed. If one instance starts failing its health checks, the ALB instantly just pulls it out of rotation.
Eliminating a single point of failure right at the door.
Right at the entrance. Exactly.
Okay, let's unpack this a bit more. The core strategy for growth. We have two methods for scaling, vertical and horizontal. Our source material is very clear which one AWS favors.
Oh, it's overwhelmingly horizontal scaling out.
And what's the problem with the other way, vertical scaling?
Vertical scaling or scaling up just means you take your server and buy a bigger one, more CPU, more RAM, but you hit a ceiling. Eventually, you just run out of bigger boxes to buy.
And you've created one massive, expensive target for failure.
You have, and you're stuck. Horizontal scaling, adding more smaller identical instances, is preferred because it's basically limitless and it's inherently more resilient.
I love the analogy from the sources. It's the difference between one massive semi-truck versus a fleet of 50 smaller delivery vans.
That's the perfect analogy. If the big truck breaks down, everything stops. Dead in the water. If one of your 50 vans breaks down, the other 49 keep moving and you just spin up a replacement van immediately. No one notices.
And we achieve that rapid scaling with auto-scaling groups.
Right.
To match supply to demand.
Precisely. And for anyone preparing for a review, it's worth knowing the policies here. You're not just saying add more servers, you're defining sophisticated scaling policies.
Like what?
The gold standard is usually target tracking scaling. You just tell the group, hey, keep the average CPU utilization at 65%, and AWS handles the rest. It adds and removes instances for you automatically. That is real elasticity.
That's a great point. But, okay, if we scale out horizontally, we create a new problem, don't we? Managing state and session data across all these servers.
That's a fantastic question, and it's the immediate architectural consequence. The answer is you have to make your application layer stateless. Meaning, if a user logs in on server A, but their next click goes to server B needs to know who they are. You solve that by externalizing the session state. You put it in a shared caching layer like Elasticache. That way, any server can pick up any request.
Okay, so we've solved scaling the compute, but now we have a coordination nightmare. The more servers we add, the higher the risk that a small failure, like a processing server going down, could cascade. We have to tackle that coupling problem.
This is where asynchronicity comes in. And this is where Amazon SQS, the simple queue service, is truly the hero.
The hero of loose coupling.
Absolutely. In a classic, tightly coupled system, the web server takes an order and sends it directly to a processor if that processor is down.
The order's just lost. Data gone. customers
It's a
unhappy.
disaster. SQS acts as a durable buffer. The web server just drops the message, the order into the SQS queue, gets an immediate okay, and forgets about it.
It doesn't care what the processor's doing.
It doesn't care if it's busy, crash, or being updated. The processor picks up the message when it's ready. The key takeaway is that the message is safe. It's guaranteed to be secure in the queue.
Okay, but what about the failure edge cases? I mean, what if a processor picks up a message, starts working on it, and then crashes? Does the order get lost then?
That's handled by a great feature called the visibility timeout. When the processor grabs the message, SQS makes it invisible to other processors for a set time. If it finishes, it deletes the message.
And if it crashes?
If it crashes, the timeout expires, and SQS makes the message visible again for another healthy processor to pick up and try again.
That's smart, but that raises another problem. What if the message itself is bad, a poison pill that always causes a crash?
You've just hit on why we have to design for permanent failure, not just temporary ones. This is exactly what a dead letter queue, or DLQ, is for. You configure the main queue to say, look, if this message fails to be processed, say, 5 times, something is wrong with it. Move it out of the main queue and send it to this DLQ. That way it can't destabilize the whole system.
So the SQS queue handles that crucial one-to-one communication. But what about one-to-many, when one event needs to trigger multiple different actions?
That's where you bring in Amazon SNS, the simple notification service.
The publish-subscribe model.
Exactly. You publish a message once to an SNS topic, and that message can fan out to any number of subscribers. This could be SQS queues, Lambda functions, anything.
That concept, one event triggering many actions, that changes everything, doesn't it? Why is that considered the holy grail of decoupling?
It's a total philosophical shift. Instead of service A calling service B, then C, then D, where it has to know about all of them.
And a failure in B stops the whole chain.
Right. Instead, service A just announces an order was placed. That's it. Services B, C, and D just react independently. A doesn't know who is listening. If B crashes, C and D keep on working just fine. The system just reacts to events as they happen.
That's true decoupling. Okay, let's shift gears to minimizing our own work, the operational effort. When should we be choosing serverless Lambda or Fargate over just a standard EC2 instance?
The critical factor is always management overhead. If your goal is to minimize operational effort, zero patching, zero server management, automatic scaling, or if you have stateless workloads, then serverless is most always the better choice.
Give us the breakdown on the options there.
Lambda is like your utility knife. It's perfect for short, event-driven tasks, resizing an image, processing an SQS message. You only pay for the milliseconds it's running. Fargate is what some people call serverless containers.
Right.
It gives you all the power of Docker, but you never have to see or manage the underlying EC2 instances. The cluster management just vanishes.
But there's a trade-off, isn't there? Isn't Lambda known for the cold start problem?
That is the key trade-off you have to know about. A cold start happens when your function hasn't run in a while, and AWS has to spin up a new environment, which adds latency.
Which for a batch job doesn't matter, but for an API.
For an API that has to respond in milliseconds, it's a huge problem. You mitigate this with something called provisioned concurrency, which basically keeps a certain number of environments warm and ready. You pay a little extra for that predictable performance.
And speaking of containers, we have to touch on the two main services, ECS and EKS. How do you choose?
Well, ECS is the AWS native solution. It's designed to just work with all the other AWS services. If you're all in on AWS and you want the lowest friction, ECS is the path.
And EKS?
EKS is AWS's version of Kubernetes. That's for a different goal. If a company is already using Kubernetes on-prem or they need a multi-cloud strategy, EKS is the answer. It preserves their existing tools and expertise.
Got it. Okay, let's move down the stack to data resilience. A resilient system is pointless if the database is the bottleneck. You mentioned read replicas and caching.
Yeah, these two are fundamental, and they both serve the same goal, to offload the heavy lifting from your primary database.
How does that work with a read replica? Aren't you just copying the problem?
Not at all. You're isolating the workload. Imagine you have your production site handling customer purchases, but you also have an internal team running heavy reports. If those heavy reports hit your primary database, they slow down customer transactions. So you point the reporting tool to its own read replica. Instantly, the workload is isolated and the customer experience is protected.
But there's a big trade-off. There's lag, right?
Absolutely. You're introducing eventual consistency. The replica might be a few milliseconds, maybe even a few seconds behind the primary. You have to be okay with that.
So you have to know your data's requirements.
Exactly. For checking if a product is just sold out, you hit the primary. For a user's profile picture or a dashboard, the replica is fine.
And caching is the next level of that, moving data even closer.
It's the ultimate speed boost. Using a service like Elasticache with Redis or Memcache, you store the results of frequent queries in memory.
Which is orders of magnitude faster than hitting a disk.
You don't have to hit the database at all for that information. It's a huge performance gain.
And real quick, Redis versus Memcached?
Memcached is pure simplicity. Just key value pairs, super fast, great for session data. Redis is more of a Swiss Army knife. It has complex data structures, persistence. If you need more power, use Redis.
Excellent. Okay, finally, let's go to the edge. CloudFront and Global Accelerator. They both seem to be about global performance. What's the real distinction?
It comes down to what you are accelerating. CloudFront is a CDN, a content delivery network. Its job is caching content images, videos, static files at locations physically close to your users.
So CloudFront caches the files near the user.
Yes. Global Accelerator is totally different. It does not cache content. It optimizes the network path itself.
The pipe the data flows through.
The pipe itself, it gives you static IP addresses and routes your traffic over the fast, private AWS global network, bypassing the congested public internet. It's about optimizing the connection, not the content.
That is a fundamental distinction. This has been a fantastic deep dive.
It's a huge area, but you're right, the concepts are surprisingly straightforward once you see the patterns.
So what's the final strategic tip someone should take away from all this?
It's simple, and it connects everything we talked about. Always identify and isolate the bottleneck. If the database is overwhelmed by reads, your bottleneck is data access. The solution is read replicas, caching. If your application is failing under load and losing data, the bottleneck is compute and coordination. The solution is auto-scaling and SQS. It's all about proactively removing those single points of failure.
That's the perfect summary. Every single thing we talked about, from the ALB to Fargate to SQS, it's all about preventing one small failure from becoming a total system failure. You're building for failure tolerance.
Tolerance is the only realistic goal. You can't be failure-proof.
Absolutely. So here's a final thought for you to mull over. Think about a complex physical system you rely on every day. Your local power grid, maybe. Where is its single point of failure? And which of these architectural heroes, the SQS queue, the read replica, the serverless function, would you deploy to force that system to fail gracefully and keep the mission moving? Go forth and architect with confidence.